All right, hello everybody. Thank you for joining us for our first Gen Chem session of the semester. Go ahead and give it over to Dr. Taylor to start.
All right, so we are a few minutes early. So we have to do something very important first that I almost forgot to do. This is my dog Riker. He got trained during lockdown that when I talk to my laptop at home, that he gets a treat. So this is a very important part of everything because he does in fact get a treat when I talk to my laptop. Um, this used to be for when I would have to do class from home and I would do announcements with him on my lap, but he doesn't like it when I just talk to my laptop. That's boring for him. So now whenever I do a meeting from home, he assumes that it is time for him to get a treat. So we have to maintain. It's a very important part of the meeting. Um, so so yeah, so hopefully you guys won't notice anything, but in the background, that dark bar is the crack of the door. So if that ever changes, that's because the small dog has widened it. Definitely not an important thing. I won't call it out again, but just in case you're curious. Um, so it's almost 5 o'clock. Um, so a couple of general things. Yes, we are recording. You'll probably hear me say that again. But yes, we are recording. And I'm going to start off this for especially this first exam review with just some general nuts and bolts of how the exam works. Folks will also put stuff in the chat. So you guys should have access to the chat. If for whatever reason you don't, that's likely because you're not signed into Microsoft Teams. Teams is kind of funky with that. But if you're not logged in, it sometimes won't let you do that. But I do also have a number of questions from my class. So if you just came here because you wanted to hang out and just absorb things, that's great. If you came here because you got a list of questions, that's great. If you're like, oh no, I asked questions on Friday, but I don't know what I asked, you can ask them again. Some of these are duplicates. Um, it's all good. So this is my preparation, which is making sure that I have enough stuff for 2 hours. The other thing that I will do, all right, so officially 5 o'clock. So the other thing that I will do is um, at least every half an hour, sometimes more often, I'll call for questions. So we do have some really wonderful folks hanging out on the call that will read those out to me. But I'm going to go ahead and get started with a couple of basic things. So what is the exam on? And when is the exam and all of that? So your exam is Saturday. It is this Saturday. So that is in fact September 20th. It starts at 10 a.m. But when I say it starts at 10 a.m., you should be there earlier than that. So be there more like by like 9:50 or like 9:45 a.m. Because you want to get there and find a seat and already have that taken care of because we will start passing out scantrons at 10 a.m. That's what happens at 10. So at 10 a.m. like we go. Um, so you want to be there early to get a seat and get everything going. Um, some things that are hanging out for you at any point. So this is the 701 section. So whenever we mention 701, that is still Chem 1311. So it has that beginning part, but then there is a 701. So I know that's a lot because y'all have labs that are Chem 1111 and then a lecture portion, which is Chem 1311.00 number. And then we also have a 701 section. But the 701 section is where a lot of things are that everybody has access to. So for example, I'm going to pull the syllabus. And your syllabus is likely also on your course homepage, but just in case you wondered, like, how do you know like what's on the exam? There is a thing that says calendar. And taking a quick screenshot so I can make it bigger. There is a place where it says what's on the exam. And so that is this thing in yellow where it tells you when the exam is, Saturday, September 20th, in exam 1, all in nice bright yellow, and it says chapters 2, 3, and then it says 4.1 to 4.5. So what that is we're going to cover most of chapter 4, but you might notice that the Monday after the exam, we're finishing chapter 4. So most of chapter 4 is on the exam, but not all of it. I know in my notes, I just have a place that says end exam one material. The other way I think about this is all neutral. So whereas this thing down here is electron configuration of ions, it's what happens afterwards. So lots of different ways to find that information, but it is on the syllabus, chapters 2, 3, and then sections 4.1 to 4.5, which is most of chapter 4. So that was on the syllabus. I also had somebody ask things like, where are office hours? That's also on the syllabus. So hanging out under contact information, there's a box that says office hours. So we have all kinds of different ways for y'all to get help with chemistry. And sure enough, coming to chit chat with the instructors is definitely an option. So everybody's got some office hours. You can also arrange one-on-one meetings by emailing us. So there's Dr. Bacon, Dr. Diekman, Dr. Hishami, Dr. Wong, and myself all hanging out. We are all in different places. Those are all of our actual personal offices, and that way we can get some stuff done. Just in case nobody comes by to see us, just in case. But yeah, but we are available at a variety of different times. So some other stuff that might be useful. This red folder that says midterm exams, useful information. One of the things that is in here is the midterm exam details. Oh, I should have downloaded that to make that big. I'll try to make that big. So I did go ahead and grab the exam rooms off of there, but let's go ahead and make that as big as I can. Insert this printout. So this is just a little one pager that tells you some general things about the exam itself. So it does have all 4 exams on it. So Saturday, 10 a.m. It's an 80-minute exam. But there will be a little bit of time in there again to pass out papers and things like that. It's multiple choice and short answer. I know one of the questions then is like, well, how much is multiple choice and how much is short answer? We usually aim for 1 or 2 short answer questions. The other thing, I'll come back to this, but the other thing that is in the 701 section is it says examples of exam blanks and keys from fall 2024. So you can also go into this folder and there are the 4 exams that we did last fall. So those are also available. So a lot of people want to see like, well, what does the exam look like and how do you write instructions and what does everything look like? And honestly, looking at the fall 2024 exam is a really good way to do that and get information on what that looks like. We're going to have an exam book and scratch paper, a periodic table, Scantron. We're going to give you all of those things. Constants, non-metric conversions, and equations. So one of the other things that we'll give you, and it'll be part of the exam booklet itself, is we refer to it as potentially useful information. But the potentially useful information is this particular little page in here. And so it's got things like going from inches to centimeters if you need that. It has constants on it, like it's got Avogadro's number and it has the speed of light. It has the calorie to joule conversion that we don't need yet, but hey, it's there. And it has a variety of equations on it. So this will be part of your exam booklet. So you do not need to bring this with you. We will provide it for you. So this will be part of your exam booklet along actually with 2 pieces of scratch paper. So the exam booklet itself will have all of the questions and the potentially useful information and a periodic table. It'll be printed in black and white. It won't be printed in color, but you'll also have this periodic table and you'll have scratch paper. So exam booklet's got lots of good stuff in it. But I definitely understand the like, but what is that? And that's where we have posted in there things that we will give you. So that's all in that midterm exams useful information of what exactly we'll give you. Other things that are on there that are useful. You need to bring a calculator, number 2 pencils, and your UTD ID or other official photo ID. So we just want to match your name to your face. That's the goal. We'd like you to know your 10-digit student ID number, but that's also if it's on your UTD ID. So if you don't have it memorized, your UTD ID's got it on there, and your metric conversions. You do need to know your metric conversions. Which metric conversions you need are also hanging out in that midterm exams useful information. It says metric conversions to know. So it's the ones that are highlighted in yellow: kilo, deci, centi, milli, micro, nano, pico. So was that 1, 2, 3, 4, 5, 6, 7? 7 metric conversions to memorize: kilo, deci, centi, milli, micro, nano, pico. That's it. Just those. All hanging out in the 701 section, so everybody has access. Things that are not allowed: no instruction cards for your calculators, no food. We do have a couple people that have peanut allergies, so no food. Do not bring it to the exam room. No books, no notes, no formula sheets. You don't need any of that. You just use what we provide you along with pencil. Nothing that no electronic devices, so nothing that connects to the internet, y'all. I don't care if they've come up with something new fandangled. If it connects to the internet, don't bring it. Also, no backpacks. This one is new. We used to allow them, and frankly, I'm just really exhausted from tripping over them and both distracting everybody around me when I trip on things, and also being terrified that I've just broken your laptop because I tripped on it. So just don't bring your backpacks. Just do not bring your backpacks. Leave them at home. You'll be fine. So you're welcome to bring a small bag, because again, the goal is for me to be able to walk through the aisles without twisting my ankle or distracting everybody because I had to make some sort of miraculous save so that I didn't break my ankle. Um, Rooms, these are your rooms. If you are one of our ARC students, this is a different room than I emailed you guys out before. I will email you again, so I'm sorry that that room number changed. This room is a little larger, which is nice, but we are all over campus. The one thing I will point out is that this SOM here, this is usually known as JSOM, or the School of Management. So if you ever look on here and you're like, I don't know what that building number is, shoot us an email, let me know. I'm happy to tell you what any of these are. I also really actually love on the UTD website. It used to be, I'll move it again. So basically I went to UTD comma map, also would have done it, but there's a campus map. And in addition to other things, there is a room locator. So if I go to different places, like if I wanted to show you where JSOM was, now it starts to focus in on JSOM a little bit. And then now I have a little option down here on the left that says view room locator. So I can view the room locator. And there is a spot where it has the floor number. So in JSOM, we're actually okay, we are on the first floor of JSOM. So I do just want 1.117 and 1.107. 0.117. So 1.117 is right here. 1.107 is over here. So really like the room locator of the UTD campus map. Super helpful for figuring out where your room is, because this is what I know how to do. This is how I find things on campus when I don't know where they are. Okay. I think that's everything on there. So we've talked a little bit about we haven't talked about any material particularly. We just talked about exactly what's covered. Exam starts at 10 a.m. Be there early. Also, a brief warning, if you haven't already noticed, our exam starts at 10 a.m. I just told you to be there at 9:45. If you live on campus, very few things are open on Saturday morning. So if you are a breakfast person, I am a breakfast person personally. You need a plan for how you're going to get breakfast on Saturday morning. That plan might be a granola bar It might be a piece of fruit that you bought from 7-Eleven the day before. I don't know. But make a breakfast plan because the dining hall opens at 10 and I just told you to be in an exam room at 9:45. So just be aware, take some planning. Take a little bit of planning. Okay, so I'm going to take a quick look at some of the questions that I got. I'm going to ask for questions in just a minute. So where can I find office hours? That's the syllabus. So we did talk about that on that first page. Will extra study material be given? I'm just going to write the word workshops and then SI under, there's SI material under my organizations. So here's the weird thing. I can show you where my organizations is. I can't show you where SI material is. It's ironic. So when you are in e-learning, I was in courses, but there's a second tab that says organizations. So when I go there, it just tells me lots of resources about how to be a faculty member. You, on the other hand, it should have something that says SI. It should have something that says Chem 1311, and it should have something about SI. It doesn't for me because I'm not a student, so it doesn't exist for me. Um, I actually just had a meeting with one of my SI leaders this morning, and she was so nice because she was like, "Can you show everybody where that is?" And I was like, "No, I can't because I'm a faculty member and I don't have access to it. So no, I can't show everybody where it is. We show you organizations. I guess it's just organizations. It doesn't say my. It just says organizations. So there is some extra study material. There's also end of chapter questions. End of chapter questions. So those are done through Alex or done through the ebook. But what we have is, it says end of chapter questions and keys. So we have both a list of questions that we recommend. You can do more than this. You are welcome to do additional ones, but I understand that time is limited. And so we have basically a recommended list for every single chapter. And then we have the keys for all of the questions. So you can do as many of the end of chapter questions out of the ebook as you'd like. So I answered this one. If your office hours don't fit, can we work out a different time? You can email me. I do wonder how people successfully get through this course. Alex textbook review, slide review, attending lectures, all of them. So I got two pieces of information on how to successfully complete this course. One, do multiple things. This sounds silly, but basically they actually did a study where they asked students what resources they used to prepare for exams. And this was, I think this was actually in a physics class. And because they were looking for the same thing, like what's the secret? Like people that did better on the exams, like what did they do? What was the best thing? And the people who did best did multiple things. And the more different things they did, the better they did. So ironically, it was not one secret thing. It was the fact that they would look at the textbook and they would go to lecture and they would go to an SI session and they would go to a peer tutoring session. So it's multiple things that helps the most. That being said, also in the 701 section, it says advice to you from spring 2025 Gen Chem students. This is a couple of pages. We just asked them at the end of the semester or last spring, like if you could go back in time, what would you tell yourself? Like what would you recommend to future freshmen? And that's what this document is. I made this one. So this is copied and pasted for the most part. I tried to organize it. Some of these things directly contradict each other because this is just from various other people somewhere. Oh, this one, the person who was like, create a system, this was pretty intense. But if you are one of those people that you wanted really specific advice, that's also in here. So I frankly don't know that I could handle all of those things, but if you wanted a system, there are people that are like, I will tell you exactly what I did. Um, so that is hanging out in here. But I do like the fact that the person who asked that question was like, I'm going to ask upperclassmen and see what they tell me. It's definitely a question to just keep asking and see what they say. I left the spring 2024 class up there too, because they were also fabulous people. That one was put together by Dr. Diekman. Maybe he pulled different quotes than I did. Um, I don't know. There's a chemistry clinic staying out in Berkner, and here's the SI schedule of SI meetings. It's all in the 701 section. Everybody's got access. It's all kinds of things. But I will fess up that the SI starts, like, there's no names attached to this, but they start at 10 o'clock in the morning and the last one ends at like 3:45. So they are definitely during business hours. Okay. Any questions so far from the chat?
I do not see any questions posted currently, but they may need a moment to fill in.
No worries. No worries. Just thought I'd ask. Okay. Somebody else asked, would you recommend reading the textbook, or is the material on our slides enough to prepare us? So some people love the textbook, some people hate the textbook. I'm a big fan of look at the pictures in the textbook, look at images or graphs in the textbook, is what I personally recommend, because again, having a chance to look at the textbook and engage with it in some way is usually good. And some people do like to read the textbook. I find a couple of people every single semester, and that's fantastic. If you can't tell from the sound of my voice, that was frankly never me. I'm not a person that can read a big paragraph, or like 5 paragraphs of nonfiction in a row, without getting kind of sleepy, which is why my personal recommendation is to look at the images and look at the words around the images and look at the graphs, because that's more engaging, and more colorful. But some people will be like, I really thought the textbook did a great job explaining stuff. I love the textbook. And maybe that's you, and you won't know unless you try it. So definitely try that. Only question I have is, how closely similar will topics covered on the first exam be the ones in previous year's exam? And somebody else, I think, also asked something similar, which was like, how do you guys write the exams? So in general, what we do is there's 5 instructors. Just so you know, there's 5 instructors. We all write 7 questions. That's 35. And then we cut questions down to like somewhere between 20 to 32. So the problem is that we don't always cut the same ones. So for example, I've been using this example all week. Oh God, it's only Monday. Anyway, like change of fact, I've been using this. I've been using this example all week. I never remember if the question that compares the Bohr model of the atom to the Schrodinger model of the atom, if that question made the cut, because we always write one. It's one of the topics that we have listed to either ask about the Bohr model specifically or to compare the Bohr model to the Schrodinger model. Those are 2 different questions. Could just be about the Bohr model, could be a comparison between Bohr model and Schrodinger model. We usually write 1 or 2 of those questions, but sometimes only one of them makes it. Sometimes none of them make it. It just depends. Similarly, I know for my class, we were talking about electron configuration today, and I was trying to point out how electron configuration and quantum numbers actually go together. So there are some exams where the people that wrote the electron configuration questions made links back to quantum numbers so that those questions read more like quantum number questions than they do like electron configuration questions. So it's a valid question to be like, well, how similar are they? I'm gonna box this thing, all 5 instructors write questions. So the topics themselves are similar, but we've got a very different set of authors this year. So last fall we had Dr. Diekman, myself, and Dr. Anka. The 3 of us wrote all last fall's exams. This semester, Dr. Anka, who's fantastic, by the way, she's great. She's just teaching labs this fall though. So she's around, but she's not writing the exams this year, this fall. So instead of Dr. Anka though, we have Dr. Wong, Dr. Hashami, and Dr. Abekon. So we have more authors this semester. You know, so similar topics, but different people writing questions, you wind up with things that look a bit different. One of my students asked, why is Alex harder than the things we do in class? I actually want to keep this in to remind you that Alex, especially in the knowledge checks, I did keep all of those sad faces, in the knowledge, which I can't spell, great, knowledge checks. In the knowledge checks, it's going to remind you of anything you got right before. So this might be picking up stuff that you remember from high school, but we haven't covered in class yet. Because I actually have a couple questions where people were asking me about things that we won't do for this exam at all, but they remembered it from high school. So now in all the knowledge checks, Alex is asking them about it. So that is something that is happening. That does happen. Are the mock exams accurate to what testing subjects will be over? I answered that one already. What's every equation or number we need to memorize? I'm going to say for memorization to look at that potentially useful information that we talked about. And I will do one particular problem that'll help demonstrate why you might need a little more than is on there. We have a periodic table on the exam. Yes, we will give you a periodic table. I'm going to come back to this one. Where will the exams take place? We're in 8 different buildings on campus. I showed those rooms. A set of constants. We took a look at that and we'll use some constants too. What should we take with us? Pencils, calculator, and IDs. Also for calculators, realize that while I am still using a TI-30X2, we already had the conversation where I don't like to fall on things that are expensive. I'm clumsy and I drop my cell phone a lot. I would also drop the calculators a lot. So I personally love this because it's like 20 bucks. I usually buy them in July when they're on sale. Also, for some bizarre reason, on Amazon, usually one color is cheaper than all of the others. I don't know why. So I love this because it's cheap and I can just keep them everywhere. If you have a TI-84, that's fine. A TI-84 will certainly do everything that you need it to do. We just don't demand it because this is fine. This is what I'm using. Equations, we're going to talk about that momentarily. Is the review covering everything on the test? No. I will not make it through everything on your exam. Even though, yes, there are times where I can be more concise than what we did in class, there is just no way that I can cover everything that we did that's required on the exam in 2 hours. Won't happen. Will not happen. How long does it take to grade the exams? I'm going to say about a week. So you're going to see grades later, usually like about a week to 10 days ish. So I'll tell you what. Okay, we talked about the practice exam. So any questions in the chat so far?
All right, so far there was one about the TI-84, which you already covered, and then there was another one asking when are SSC exam preps?
Oh, cool. Fabulous. So the only one about the Student Success Center that I know Dr. Diekman actually found out Got to admit, I did not have the answer to that, but that is hanging out in the 701 section as well. So Wednesday, September 17th from 7 to 9 p.m. Location right now is to be announced. So none of the instructors right now know this answer, so that's why it says TBA. Student Success Center is doing something. So that's what we know. If you guys know and you want to put that in the chat, by all means, do that. And we would be happy to update that for everybody. So we try our best to let you know as much as we know. Also, the last minute Q&A session. Sorry, Dr. Diekman put this up here. Friday from 2:30 to 4:30 in Founders North 2.202 in person. And then the chemistry clinic has scheduled hours as well. So yeah, so this is all in the 701 section under the announcements tab. And we will keep that as updated as we can. So one of the questions is about things like equations I need to know. So what I wanted to do was, sorry for all the scrolling. I'm going to go ahead and grab that potentially useful information. And then I'm going to go ahead and write a question so that we can talk through both what information is on here that's useful and what information I actually either need to know or bring in. So also let me do a couple different things. I will make this larger in just a minute. Cool. Okay. So the question we're going to answer is, what's the wavelength associated with an electron that falls from n equals 2 to n equals 1 in a neutral hydrogen atom? It's not how you spell neutral, but you know what? We're going to roll with it today. So a couple of things. One, this does say neutral hydrogen atom. So this is supposed to be my reminder that we are in fact talking about basically the Bohr equation is what we're going to use. Also the fact that all I have are n's. All I have are n values. This is the only information I've got is that my electron starts at 2 and goes to 1, and that's all I know. And I'm supposed to come up with a wavelength for that. So that will take some steps to do. So for that, I need the Bohr equation. So I'm going to come over to my potentially useful information, and this here is the Bohr equation. I need to be able to see all of my stuff at the same time. This is the Bohr equation. So this is the thing I'm going to use, but I'm not going to use that thing with the pi and the, no, I'm not going to use that. I'm just going to use E equals negative BZ squared over N squared. That's what I'm going to use. So notice that it doesn't actually tell me what that lowercase n is. It does actually tell me what B is. So I have a lowercase b here and I have a lowercase b here. And it does say constant for Bohr model hydrogen atom. So that it does give me. So that information I do actually have, but I have to put all that together, that lowercase b and the other lowercase b are the same, and those are the things I need. I do need to know what Z is though. And depending on your section, you might have been taught different things. There's two different things you could have remembered. One of those is, sorry. So good news and bad news with OneNote. Good news is I have all the space I need. Bad news is I have so much space that I sometimes can get a little bit turned around. There we go. So when I'm talking about a value of Z, I'm actually talking about my number of protons. So Z is the nuclear charge, which is also the number of protons. It's hydrogen. This says it was a hydrogen atom. So Z has to be equal to 1. In your section, you might have also covered the fact that essentially for this equation, we're always going to use Z equal to 1. And that is still true because, well, yes, you can technically use this for other 1 electron atoms. This math problem will be long enough without making Z be different things. But you need to bring what Z is to the table, where to find B, and what N is, but N is in the problem. So the other thing you might notice is that I have 2 different values for N, but this equation only has 1 N present. So this is where the way that I teach this, so there may be other ways, but the way that I teach this is that change is equal to final minus initial. So when we talk about this, what I have here is that it's falling from n equals 2 and it's going to n equals 1. So from means that this is the initial. 2 means that this is final. What I can then do is make a slightly modified equation. So I've got the change in energy is equal to negative B over N squared final minus negative B over N squared initial. So change is equal to final minus initial, and all I'm doing is putting in my N's. So that means I've got negative B over N squared final. My final is 1 squared plus subtracting a negative means that this is now adding. B over my initial is 2 squared, or my initial is 2. My initial is n equals 2 squared then because of the equation. So I do have to basically have some general idea of what I'm doing. So getting from the potentially useful information to this point does take some practice. And that's a lot of how you're going to know. So one of the questions is, how do I know which equation to use and what information am I going to be given? You are going to have to practice enough with the different equations to have a general idea of what your options even are. The other thing that you might notice is everything I have right now is all about energy. The question, though, asked about wavelength. Wavelength is this thing, this lambda. So wavelength is over here. Between Alex and end of chapter questions, your job is to know that you can use this middle equation to go from energy to frequency and then go from frequency to wavelength. So we're actually going to use 3 different equations in this one problem, and we're going to use a different constant for every one of them. I think I mentioned this is a long problem. It's a long problem. But I've got a couple reasons why I wanted to do this. From here, we're going to keep going. This math then kind of depends on how you like it. So this then is the change in energy is equal to negative B over 1 plus B over 4. And at this point, we can plug things in or deal with it. But B is 2.180 times 10 to the negative 18th. So I was not really going to deal with that until I had to. Minus plus 1/4 times 1/8 times 10 to the negative 18. And there are different ways to do this algebra. There are. So if you had a different way to rationalize your way through it, that also works. At the end of the day, I get a change in energy of negative 1.635 times 10 to the negative 18. That's in joules because my B is in joules. I'm going to do two different things. That is in joules. And then this is the part where it's like, I did prepare. I am cheating a little bit in that this is a question I did for workshop. Okay. Good. It's the same. It matches my key so far. So now I need to go. So I have energy. Maybe that was the question. I have a negative sign here. This negative sign means that energy is released. We also use the word emitted, or sometimes the word emission, but it's leaving the atom. As my excited electron goes from a high energy state to a lower energy state, it releases energy or emits energy. But that's not wavelength. So what I need now is I have different equations. I'm going to write them down here, and then I'm going to go back and show you where these are on the potentially useful information page, because these are both from the potentially useful information. So I've scribbled a lot all over this, but here is my energy equals H times nu for the frequency. So, yep, so I need an H. And I'm apparently highlighting this one in red. So I've got an H here and I have an H here. So this H is this H down there. I also have, trying to do it, do I have two different colors? I also have a second equation I need that has wavelength in it finally, and that's got a C in it. And I've got a C right here. It's the speed of light. So this is that thing where you have a PDF file posted online. This page will be in the exam booklet itself. You might also get a hard copy so that you can practice this off of a piece of paper, because all the information is there. But utilizing it, knowing where it is, being comfortable with where it is another story. So I have energy, we're going to go to frequency, we're going to go from frequency to wavelength. So one of the weird things though is this energy is negative, which means that it's released. From here forward, I am going to take the absolute value of that because when I go to wavelength especially, this is going to be in length. It's going to be in meters or nanometers or something, and negative nanometers don't make any sense. This must be a positive value. Frequency also should be a positive value because frequency is in a per second. It's in a per unit of time. So frequency also should be positive. So what I'm going to do is I'm going to rewrite my number, but as I rewrite this negative 1.635 times 10 to the negative 18 joules, negative 18 joules, right? Yes. Okay, good. Yes. I'm going to take the absolute value so that I have a positive number, because once we get out of energy, negative numbers don't mean anything. So negative energy gives us direction, and that's fine and dandy and good. But once we're out of that, I need this to actually make numerical sense. So no more negative numbers once we're out of energy. I need numbers that mean things. So I'm dividing both sides by Planck's constant. So this was my energy. This is H. So I'm solving. So I'm dividing both sides by Planck's constant. This gives me a number of 2.468 2.8 times 10 to the positive 15th. That's in a per second. Since this is frequency, I could also say that this is in a hertz. And that means the same thing. So frequency does have two different units that are identical. You have my apologies that we also use in some guy's last name as well as the per second. Personally, I like the per second, but I didn't write the frequency questions. Wait, did I? Oh God, I don't remember. I did write one of the frequency questions. I'm sorry. This is what happens. So anyway, so good news, bad news. Two things. One, I've taught General Chemistry 1 every single fall since I was hired. So I have taught Gen Chem 1 every fall since 2013. So that's a lot of Gen Chem, right? So I sometimes have problems remembering which semester is which is why you see me grab documents off of e-learning so that I'm not wrong and I'm not lying. I just grab the documents off of e-learning so that I make sure I do it correctly for this semester. Two, this does also mean, and I gave this to one of my classes already, I know, if you ask me a question, I will just answer your question. Tomorrow, you can ask me the exact same question again, and I will put a smile on my face and I'll just answer your question again. You can ask me you can repeat that on Wednesday and Thursday and Friday of this week, and I'll just repeat myself. That does mean that if you need a different explanation, you need to tell me, hey, Dr. Taylor, you already answered this one way. I need you to give me a different explanation. And I will just look at you and go, oh, okay. And I'll give you a different version. Because I do have different ways of explaining things, but I have favorites. And so I do those first. And I can't remember who I've answered what as we go along. My goal is wavelength, and I'm not there yet. So we're going back to my potentially useful information with this equation that has been scribbled all over and a value of C that's still coming from this page. So as I now go to write my equation, I'm copying it from above. So C I'm taking from the potentially useful information, 2.998 times 10 to the 8th. That's in meters per second is equal to wavelength, the thing I actually wanted, times my frequency, and that's the thing that I'm copying. It's 10 to the 15th. And we'll go ahead and write those seconds to the -1 so you can see those cancel out. And again, I divide those sides by that. And for wavelength, I then get 1.21 times 10 to the -7th meters. And the question, I think it just said, what's the wavelength associated? So it didn't actually ask me for nanometers or meters, but I know some people would like to see some metric conversions. So we're going to go ahead and convert this to nanometers. So this is the part you have to have memorized. So 1 times 10 to the -9th meters is 1 nanometer. I'm going to go ahead and do the math, and then I'll show this off. So I am dividing by 1 times 10 to the -9th. I have to have my meters in a way that will get rid of the meters. So I can cancel them because of the way that I have them. One divided by the other will make the units cancel. So I'm making the meters cancel because I don't want those anymore. And the only thing that I have left over are nanometers. It gives me 121 nanometers by the time that I'm done. Now, the reason why I went ahead and I got that 1 times to the -9th meters is because while you're going to have all your metric conversions memorized, did I get there? Yay! I got there. Oh, maybe, yeah. Great. Well, you're going to have all your metric conversions memorized. Remember that we've got a particular list for you to know. And the particular list essentially has everything written. I'll take a screenshot so I can make this bigger. Has everything essentially in terms of the meter. So when we look at the list that's posted, hey, that's a, oh, darn it. I am not going to dig through my screenshots to find the right one. I'll just do it again. Yay. So what you might notice is you might notice that all of these, even the one that you're responsible for that's bigger, the kilometer, those exponents go with the meter. So a kilometer is 1 times 10 to the positive 3 meters. A nanometer is 1 times 10 to the negative 9th meters. A millimeter, 1 times 10 to the negative 3 meters. So that conversion factor in this table is always going to the meter. So one of the questions I often get is, in a metric conversion, how do I know where the number belongs? And for this table, the number always belongs in the base unit. So if you're in liters, it goes with liters. If you're in meters, it goes with the meter. If you're in hertz, it goes with the hertz. So whatever the base unit is where that belongs. As far as whether you multiply or divide, you divide to get rid of the unit you don't want. So in this case, we didn't want the meter anymore, so we divided by the meters. So you divide by the unit you do not want any longer. So you divide, you usually are trying to get rid of, you want the unit to cancel. The goal is to get the unit to cancel. So watch where your numbers are, but the goal is to get the units to cancel. So some things I wanted to point out and why I chose this problem. Couple things. One, personally, I think this is the longest math problem on the exam. So for those of you that were like, wow, that was a lot. I agree. There were a lot of steps. The thing is, about our exams, a random number generator puts these together. So if you see what's the wavelength associated with an electron that falls from n equals 2 to n equals 1 in a neutral hydrogen atom, you might be like, I can definitely do that. I got the steps down, but that's a good solid 3 steps. Maybe you want to do that not first. Maybe you want to skip around the exam and save something that will take you more time later and do something that's shorter that you know that you can get done in a short period of time. And you might do that first. It's your 80 minutes. All the multiple choice questions are worth the exact same number of points. So this question that might take you longer is worth the same number of points as something that's asking you to identify how many protons, neutrons, and electrons are in something, which is usually a more straightforward question. So just keep that in mind as you go along. I also use this question so that we could use multiple equations out of here and get a general idea for looking at constants, looking at equations, things like that. So that was another reason I wanted to pick that particular problem, is so that we could utilize actually all 3 of the equations, because even though there's more questions on here, you're not going to use the other ones. This one has to do with kinetic energy. And while it's a lovely thing, we won't actually use any calculations for it. This one is for potential energy. And while you should know what potential energy is, we're also not going to calculate it here. This one is the one that goes in between wavelength and velocity. And we don't do calculation questions with wavelength and velocity anymore. So also don't use that one. Okay. Any questions so far out of the chat?
All right, so we've had a couple come in over the last 20 minutes or so.
Great.
One person had another calculated question asking if they could use the TI-83 plus.
Yeah, TI-83 plus is great.
Sweet. The next one was, can you go over orbital shapes they gave the examples of 2px, dxy, dyz, and asked how those work.
What else?
Next was, can the formula also be written as, so it's one of the ones covered, but it says E equals negative B, and then in parentheses, 1 over n to the power of 2 final minus 1 over n to the power of 2 initial.
Anything else?
Next is, where did these, oh, well, this one, they asked where did the z go in a particular equation, but it does not state which
I
equation.
can take care of that though. Yeah.
All right. Another one asked, where did the 1/4 come from? These are both from 15 minutes ago, so whatever was covered there.
No problem. I know where that is.
All right. Another is, what is V in the C equation?
Okay. What else?
Another is, for the metric conversion for the wavelength problem, it's fine to do 10 to the power of 9 nm over 1m.
Other things.
All right, next was, how do we do sig figs for questions like the one we just did, where the only number given are the n values?
What else?
There's another one, why doesn't the exponent get changed to a positive when using absolute value?
It's valid.
There's a
Right.
Another one is, do we need to know any other orbital shapes beside the S and P subshells?
Thanks.
All right. Another student asked about the TI-84, which you said yes to already. And then the can you please help with writing electron configuration for an atom using the periodic table?
Absolutely.
And I believe that is all for the moment.
Cool. Okay. So I'm going to start with questions that were on the calculation that we just did. So while I'm definitely all for orbital shapes, we're going to come back to that in a minute. So somebody gave an alternate algebra version of the formula. Yes, that also works. I always take a minute because negative b over n squared final minus negative b over n squared initial. Yes, so this basically takes out negative b. And so this is a different algebraic rearrangement. This works just fine. There are multiple different algebraic versions of the change in energy equation. So yes, this one does also work. This is just a different algebra version, but yes, this is valid. This works just fine. Where is Z? I apologize that I took that out. So we're back on taking the equation from the potentially useful information where there was Z. My question stated that I had a hydrogen atom. So Z is actually equal to 1. So really, I should have put 1 squared in here when I did all of my math, but anything times 1 is just itself. So that's where Z was, is I basically left it out because B times 1 is still just B. But you're right, I did just magically make that go away, and it would have been better to showcase what happened to it. So valid point on the Z. Someone wanted to know where the 1/4 came from. So anytime that I'm using this equation, because there are different algebraic ways to do this, some people like different versions better than others. But basically what I did is I took 1 squared and said that that was 1. So 1 squared is equal to 1. And so that's where this 1 went down here. And then 2 squared is equal to 4. So that's where the 4 came from there. So that way, when I was putting things out. This is basically negative b plus, and then this was my algebra version of how I thought about it, is I turned b into a number, and then this is then basically b over 4 is the same as 1/4 times b. So that's just another way to do the algebra. It's another way to write it out. So you're right. I could have also written that out as, so the other way to write that would have been 2.18 times 10 to the negative 18 divided by 4. So same idea, but a different way to write that. So apologies that that was not clear as we went through. So in going back over the math, a lot of this is kind of a preference in what your algebra looks like. So this is also where I would highly encourage you to try it out on your own, because multiple ways are correct. Multiple ways to do this are correct. Okay, so we talked about Z and we talked about the 1/4. The V, so when we're looking at, oh gosh, didn't realize quite how messy those got. So I'm gonna redo this just so that you guys can actually see, because I don't know after all that scribbling if it's obvious. Okay, so we're talking about these two equations and this letter. So this is a Greek letter, but this Greek letter is supposed to be frequency. If y'all have ever had a physics class, likely you guys use the lowercase letter f, and I like that better, but this is what your textbook uses, so this is what we use. We are in line with your textbook, so that nobody asks what that other equation is. So it's the exact same as what's in your textbook, but that particular letter is supposed to be frequency. So when we were using units that had s to the negative 1 or hc, that's frequency. So that's what those two letters are supposed to be. But yes, if you'd had a physics class, you'd probably used a lowercase letter f. And I really wish that that's what we used, because I personally would like it better. But you can in your notes, but this is what's on the potentially useful information page. So, and it does match your textbook. And oftentimes, even in my notes, when I would prefer a different variable, I will stay in line with your textbook. Somebody called out the fact that there is another way to do metric conversions. So I'll show this off really quickly. So some people like this and some people don't like this. So what we have posted on the 701 page shows that 1 nanometer is 1 times 10 to the negative 9th meters. If I said this in words, this means 1 nanometer is a very, very, very small piece of a meter, right? I'm saying I have 1 nanometer, and 1 nanometer is a really teeny, 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 tiny little piece of a meter. That's what this math means. That's what those numbers mean, is that 1 nanometer is a really, really small part of a meter. You can say this the other way, which you can say that, by the way, I need a lot of nanometers to equal 1 meter. I get spoiled because when I work at home, I don't have, the end of my stick is not an eraser. So this in red basically says it takes a lot of nanometers to equal 1 meter, which makes sense, right? A nanometer is a really small part of 1 meter. So if I wanted to make a meter out of nanometers, I need a lot of them. It's kind of like asking if I wanted to build a house out of Lego bricks. And Lego bricks, they're like smaller than my finger, right? So I would need a lot of Lego bricks to build a whole house. I could also say that if we're talking about a house made out of Lego bricks, that one Lego brick is a very, very small part of the house. So both of those work. Both of those work just fine. It depends on which one you're already familiar with. If you're not familiar with either one, then it kind of depends on you, and which way you personally prefer. But both of them are fine. Both of them will get you to the exact same place. Both work great. Okay. Sig figs within. So first of all, I'm going to say this: sig figs. We do not test on sig figs in Chem 1311. We don't. We do not test on them. So it doesn't matter. In a multiple choice exam, all of the answer choices will have the same number of sig figs. You won't get to pick, because we will not test you on sig figs in 1311. We will sometimes, if it's a short answer, we'll sometimes ask you for multiple digits, just so you don't round and only give us one. But it doesn't matter. In case you were curious, you can watch me not write this down. The question, values of n are what we refer to as exact numbers, which means they have an infinite number of significant figures. So n equals 2, that's not one sig fig. N equals 2 is an infinite number of sig figs, because there's no such thing as n equals 2.0. It's not a thing. N is equal to 2, and that has an infinite number of significant figures, which means for this problem, if I was doing significant figures, I would actually be limited by my constants, which is rare, by the way. But the constants would actually limit the number of significant figures. You would be stuck with the fact that this only has 4 significant figures. All of these have 4 significant figures. You would be stuck with a maximum of 4 significant figures, because that's where your that's where the sig figs would come from, with your constants, which is not normal, but in this case, that would be where that would come from. Okay, why didn't my exponent change when I had absolute values? So the negative 18th, that's because scientific notation is just a way of communicating faster. So what I mean by that is negative 1.635 times 10 to the negative 18th is really negative 0.123456789 10 11 12 13 14 15 16 17 1 6 3 5. Almost can't get it all on the same screen. This number. So I was trying to take the absolute value of this number. When I take the absolute value of this number, I just want it to be positive. 0.123456789 10 11 12 13 14 15 16 17 1 6 3 5. That's what I want. I want that number to just be positive. I don't want the exponent to change, because this should still be a very, very small number. So even though my exponent is negative and I applied an absolute value sign, I don't change the exponent, because this number should still be tiny. It should still be a very, very small part of a joule. I just need a positive value so that I get to wavelength and I have a positive wavelength. But valid question. Okay. Answered all the questions about all the maths. Before we move on from math stuff, I want to point out one quick thing, which is while we do give you Avogadro's number, it's right here. We give you Avogadro's number. We have that. Notice that grams to moles is not on this list. But grams to moles conversions are absolutely things we can test you on, but there's no equation for grams to moles. Average atomic mass. We can absolutely ask you an average atomic mass question. There is no formula on this page for average atomic mass. So just be aware that there are really only 3 equations that we're going to ask you to utilize, but there are conversions and there are other mathematical things for you to be able to do. But I got multiple questions about orbital shapes. So we're going to do orbital shapes, which are super fun. Okay. So orbital shapes, orbital shapes. The other thing I'll say real quick is for any of y'all that either saw some of the questions that I had posted and you were like, no, she's not going to do them. I will make a follow-up video and go over this. So whatever my class asked, I will do those, or as many of them as I possibly can, because at some point I will run out of time, and it's better to post a video that's only 2 hours long and doesn't go over everything than a video that is 4 hours long, but that you don't get in enough time. Orbital shapes. Doing orbital shapes. Okay, so first of all, when we talk about orbital shapes, these can be asked about in a couple of different ways. So one option is to talk about things like the s orbital, which is a sphere, by the way. And yes, when I draw it, it looks like that. It's a circle. So this could be an n equals 1, l equals 0. There's my shape. We could also call this the 2s. There's my shape. I realize that would be a different value. That would be an n of 2 and an l of 0. There's my shape. So we can call this a couple of different things. I could throw my m sub l value on here. That's a 0, that's a 0, that's a sphere. That's a 0. So I have different ways that we can still talk about that shape, but that's still s. I could put that on a coordinate plane. Here's my x, here's my y, that's my shape. It would be nice if it was centered on my plane. That's slightly better. You know, options. So that's one of them. So you should know that one. Sorry, my dog is making what I refer to as sad sounds because he thinks that we should be doing something else. Too bad. We could talk about p orbitals. So this would be things like n equals 2, l equals 1. This also would have 3 different values of m sub l, which means I also need 3 different orientations. So I should be able to have a px orbital. Here's my x-axis, here's my y-axis. My px orbital is on the x-axis. Yes, you should be able to know that the px orbital is centered on the x-axis. You should know that. If I'm asking about a py orbital, this is going to be centered on the y-axis, and it looks kind of like that. The last one, perhaps unsurprisingly, is the pz orbital. So if this is my x and this is my y, it should be coming out at you, and then it's centered something like that. And that's my pz, because that's my z-axis. And yes, we could just have a different orientation, and this is my x-axis, and this is my z-axis, and then my orbital looks like that, and that's still a pz, because now I have labeled the z-axis on my axis. No, that's not all the shapes. Also, while yes, you do need to know that the px orbital is centered on the x-axis, the py orbital is centered on the y-axis, the pz orbital is centered on the z-axis, and that its values and that p therefore belongs to an l equals 1. which means that each one of these different orientations of a p orbital relates to a different value of m sub l. You don't need to know which value of m sub l belongs to which one. So which one of these is an m sub l of -1, and which one is a m sub l of 0, and which one is a value of +1 for m sub l, you don't have to know that. I don't know that off the top of my head. I have that written down somewhere, but I didn't put it in the notes because you have enough stuff to know. It may seem like an arbitrary line in the sand, but that's the line in the sand. But that's not all. We can also do n equals 3 and L equals 2 d orbitals. This is the last set. So when I do d orbitals, so this is I'm going to double check. So these are the ones that, because there's 5 of them, I want to make sure that I get them correct. And also, some of my classes have seen me draw things poorly. So it is also nice to have a textbook image because my images are okay. So I will still draw them by hand just to demonstrate what we're looking for. But I am definitely also going to try to get a helping hand because maybe this image is better for you. So that means I have m sub l values of -2, -1, 0, +1, and +2. So 3 of these are in a plane. So we're going to go back to drawing x's and y's. So I'm actually going to draw the 3D xy. So here is my x, here is my y, and this is a clover leaf that is in the plane like that. Clover leaf like that, close enough. So that's my dxy. However, the 3dx² minus y² looks very similar because here's my x and here's my y, but it's basically shifted about 45 degrees because this is actually now centered on the axis. Really? Sorry. That's better. So the dxy is in the xy plane. The dx² minus y² is centered on the axis. Therefore, the dxz and the dyz are also going to be in the plane, but they're also going to be just in different planes. So this is the part where when I draw this, the axis that I label becomes the important part, because honestly, this could look the same. But these are supposed to be clover leaf shapes. 3D, YZ, and here's my Y, and here's my Z, and look at me draw the same cloverleaf shape. The only one of these that then is different, so all these are cloverleaf shapes, they're supposed to be 4-leaf clover shapes, except for the 3DZ² shape. That one is centered on the Z axis, so 3DZ². Notice it's the only one that only has one variable in it. It is therefore the one that is centered on the Z axis, but it has the donut that goes around it. When I draw it, it looks like that. If you have never seen them before and you don't like my drawings and you don't like the 2D shapes, the two-dimensional shapes, one of my personal favorites, the website is called Orbitron. Apparently it's also a font, but this has some really lovely images of what these look like. So there's the thing I was trying to draw, which has a donut around it. So it's a better 3D rendering. We obviously don't expect y'all to sketch a 3D rendered thing. But I just know for some folks that having better images often helps. So this is available. It's a free website. I think it's the dots that you can drag. Yeah. So I can actually mouse over and drag this one around, and I can drag this one around too. So if you're trying to get a better handle on the 3D nature of these, some of these websites may help just in picturing those a little bit more. Oh, that went away. So there's some help for you guys with the shapes. Also, so as far as the exam goes, these are the shapes we hold you to. So S being a sphere, T having 3 orientations, D having 5 orientations or 4 orientations and 1 other shape, depending on how you want to think about it. That's what we hold you responsible for shapes. Some people are just curious. I think the reason why I like the website is that you can take a look at F if you want to. It might then be obvious why we don't test you guys on F. F is even more difficult to draw in a exam because there's a lot of slices happening in wonky waves. But again, if you wanted to play around because you were curious and you want to see what those look like, they are pretty, but they are interesting. And you need more and more some sort of 3D rendering tool. So S you can handle in 2 dimensions. P you can do 3. D you can do, and after that we need some shading. We need some artist renditions because it gets too complicated. Too complicated. Okay. The next thing somebody asked for was electron configuration. Yay! Let's do electron configuration. We did orbital shapes. We did TI 83 plus. Electron configuration. So let's do a fun one. But also a valid one. So something fun, but not too much fun. Let's do Mercury. Yeah, I went that one. I went Mercury. Z equals 80. So oh God. Oh yeah, we're gonna wait. I'm sorry. Wait. We are also gonna do argon first. Yeah, we're gonna do argon first and then Mercury. Because argon will let me show off how this works in general, and then Mercury will let me answer most follow-up questions about electron configuration. But that way I can also do the arrow thing without me being real mad at myself. Okay, argon. Calcium? Argon. What do we do? Argon. I already highlighted it. Argon. So what we're gonna do is we're gonna do electron configuration, but I'm gonna do electron configuration first and then orbital notation because we asked for electron configuration. So I'm gonna start over here. This says 1, it's very small, but this says 1, this says 2. The other fun thing that is also present here is this. Oh gosh, what is wrong with my pen? This thing we often also refer to as the S block. This one way over here is supposed to be the P block. There are pictures of this online, by the way. This thing in the middle is supposed to be D. This thing down here is supposed to be F. So as I go from left to right, I'm going to start with 1 and S because that's what that block is. And then there are 2 blocks, hydrogen and helium. So 2. Then I'm going to go to the next row, 2, and also S. And there's 2 electrons that fit in the 2s subshell. And then I'm over here, which is P. But I'm still in 2, so this is 2P, and it's 6. 1, 2, 3, 4, 5, 6 fit there. Now, I also know how many, so I'm going to keep going and finish the electron configuration, and then I'll show you guys the arrows and how we know. how many electrons fit in there. Then I'm back over here to a 3 that I covered up, but that should be 3s2. And then to get to argon, I'm going to 3p and 6 because argon's way at the end. So 3p6. And this is argon. Now I could have also done that with arrows, in which case it looks like this: 1s, and I put 2 arrows in, 2s, and I put 2 arrows in, 2p, and I put 6 arrows in, 1, 2, 3, 4, 5, 6, 3s, and I put 2 arrows in, and 3p, and I put 6 arrows in, 1, 2, 3, 4, 5, 6. When we're talking about all of this 1 is my value of N. This S is my value of L. The fact that I have 1 blank right here is the fact that I have an M sub L value and I only have 1 value of M sub L. The fact that I have 2 different arrows are my values of M sub S. Positive 1/2, negative 1/2. They are all here. So all of your quantum numbers are represented. So this 3p, there's my value of N. P, there's my value of L. And then I've got 3 blanks. I have, when L is equal to 1, I have 3 values of M sub L. So I've got a -1, a 0, and a +1. That all the quantum numbers are here. So as far as how do you know how many orbitals are in the 3p subshell, even though it looks like it's an electron configuration question, that's really a quantum number question. Electron configurations come from quantum numbers. So the reason why I wanted to do argon is because we also have what we refer to as a noble gas configuration. So for example, if I want to do the very next thing, which is potassium, has 19 electrons, that would just be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So a couple things. One, yes, it's 4s1, even though the n equals 3 shell does have d orbitals. 4s1 is what's next. But the other way to write this, because the electron configuration for argon is just hanging out in there, when I want potassium, I could just put a box, a bracket, and put argon and then 4s1. And this works for the electron configuration of potassium. I had some questions in class, and one of them was like, so if you ask us for the electron configuration for argon, can we just draw a bracket around argon and call it a day? We're not going to ask you for the electron configuration of just a random noble gas for that reason. So we might ask you for the full thing. We might ask you for the shorthand. You should be able to utilize both. Now, I did all of this. I do also want to go ahead and do mercury. And here's why. So when doing mercury, what I'm going to do is I am going to go ahead and start from xenon to show off the fast way to do this first. So the goal is mercury. Goal is Hg. C is equal to 80. So I can go ahead and write the noble gas configuration of neon, or just write noble gas neon, and then I start over here. This is 6s2. Then I go ahead and do the 4f before I forget. This is 4f14. You can also count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can count how many there are. You can also say that when n is equal to 4 and L is equal to 3, that's the f orbital. M sub L is equal to -3 and -2 and -1 and 0 and +1 and +2 and +3. And that's 1, 2, 3, 4, 5, 6, 7 orbitals. Each orbital holds 2 electrons, 14 electrons. That's how you get to 14. But you can also just count them. But that's also where that comes from. 4F14, then 5D10. So this is, and that gets us to mercury. So this is the weird thing about doing electron configurations is you do need to know that in that row, while yes, we do get to deal with F, that is the 4F. It's not the 6S, 6F, it's the 4F. 4F is correct. Same game, it's the 5D. I had some people asking me if the order of these mattered. They do not. So if you are writing this out because it's a short answer question, you can write this in whatever order you want. Now, granted, the 6 and the S and the 2 have to all go together. But I have seen people who were taught that this should go in this order. That the 4 goes first, and then the 5 goes, and then the 6 goes. That's fine. It's fine. As long as all the pieces are there, it's fine. You're going to see us go in periodic table order, and we usually go ahead and do the F before the D because of the periodic table. But either order is fine if you are writing it by hand, but you're going to see us use the one that I wrote first, where you go 6S2 and then 4F14 and then 5D10. Notice that I also picked an example that does not land me in the F block. We will hold you responsible for 5 exceptions to electron configuration. Did I scribble all over my exceptions? I did. The 5 exceptions are chromium, molybdenum, copper, silver, and gold. I'll talk about the exceptions in just a minute. But those are the 5 exceptions you are responsible for. There are more exceptions than that for electron configuration on the periodic table. There are. But those 5 are the only ones that we will test you on. The F block has a lot of exceptions. And in general, what we try to do is we try to ask you questions that not only use the rules we taught you, we also try to ask you questions that in real life act on the rules we taught you. So while sure, we could ask you guys for the electron configuration of gadolinium, it's in the F block. You could follow the rules, you could get me an answer, but because there are so many exceptions, especially in the F block, you wouldn't necessarily know if that was correct. You would know it would be okay by the rules we taught you, but we just frankly prefer not to land you in the F block because there's so many exceptions. So we will usually land you in the D block, the S block, the P block, but we won't land you in the F block because things get really confusing really fast. And again, just they usually have more exceptions than follow the rules. I can still talk about the exceptions, but before I do that, it's 6:30. Are there other questions out of the chat?
Okay, so I think we have a few more questions. One was, could you go over quantum number?
Okay.
Another was, can you go over valence electrons and ionization energies?
Okay.
Another was, since the Bohr equation is only applicable for one electron atoms, will Z always be 1? Or will it be greater for 1 electron ions?
Okay.
Next is there a technique for calculating or remembering going from grams to moles, moles to grams to atoms, and vice versa?
There are things.
Someone had a comment about the Lego bricks. But then there was, where can we find the past exams from fall semesters? That's another one.
There are things.
All right. Next is what kind of exam questions would be about the orbital shape stuff?
Okay.
Checked. Will we be tested on exceptions to typical electron configurations such as gold, silver, or copper? Uh, when we're writing the electron configuration, does 4s go before or after 3d?
Okay.
Next is, will we have a question where we'll need to differentiate between metals, nonmetals, and metalloids? And if so, will a periodic table show which element is which in the block?
Okay.
And then the last question was to please go over the exceptions, which I think may have been covered already, or at least someone saw it already.
Stories. Other things.
I believe that is all at the moment, except oh wait,
Cool.
I missed this one. Do we have to have all these shapes memorized for S to D?
Cool. Anything else?
I believe that is all at the moment. Oh wait, just one more just came in. Okay. Someone said, what is Z in the Bohr equation?
Okay, cool. Anything else?
Let me refresh again. Looks like that's all at the moment.
Okay, so going out of order. Do you have to memorize all the shapes? S, P, D. Yes. Yes, you do. That was why I covered all of them and drew the axes. Yep. Yes. Yes. Yes, you do. What is Z in the Bohr equation? Z is nuclear charge, which is also the number of protons. So depending on what source you're looking at, sometimes you'll see it listed as nuclear charge. However, every proton has a charge of +1. And when you're talking about the charge of the nucleus in chemistry, we just mean how many protons are there. So yeah, sometimes we're fancy and we're like nuclear charge. It's just the number of protons. And that is the reason why the person that was asking about in the Bohr equation that we're using hydrogen, basically, are we always going to use hydrogen? Yes. So that's why Z is going to be equal to 1, because we are just going to use hydrogen. That equation question is long enough as it is without it. Since we're on kind of orbital shapes and stuff we did in the past, what do exam questions look like on orbital shapes? So there are, there's, depends on who writes it, right? So we can ask you to draw it. We did that one year. We ask like draw the px orbital, and put it on an axis, and you had to draw it. So it was a short answer question one year. We can give the shape, and ask if it's S, P, or D. We can give you a shape, and we can ask you for the value of L, because every shape has both a letter and a corresponding number of L, so that will also work. And we could do these in the reverse, right? So we could also give SPD, whichever one we're doing, and we could have multiple choice options with shapes. And so therefore we could also give quantum numbers. And then the options, the multiple choice answers for all shapes. That's 5 different ways to ask one question. That's all I got right now. We can ask the other instructors and see what else they got, but that's what I can think of. And so it really is like multiple choice questions. There are different ways to ask that question. So that way A could look like this and B could look like that's supposed to be a clover leaf. I would obviously actually grab the actual art. And C would be the donut one, and D would be a sphere, and E would either be nothing or would be a different axis or something. And then you say if n equals 3 and L equals 0, what is the shape? And I realize that with my quick handwriting, it might not be obvious, but when L is equal to 0, I'm looking for a sphere because that's S, and that's what this is supposed to be. I understand, since I drew them all by hand, you might not agree with me, but that's an option. So there's lots of different ways to write that kind of an exam question. It is always a good question to be like, what might this look like? And this is one of those games where you can take a look. Somebody asked where they were, so I'm going to show off. I'm going back to the 701 section. And in the 701 section that everybody has access to, that's why I'm in the 701 section, not in my personal lecture section. I'm in this exam section that everyone has access to. One of these says examples of exam blanks and keys from fall 24. And it says blanks, fall 24. And that's what I would recommend you look at, because you would do better if you tried to take last fall's exam and see what you currently know and see where you are. But you can take old questions from there and basically ask, well, how can I basically like twist this around, or like what are other words that they could change out, or what are other phrasings that I might have seen, or what else could this look like? Because there's lots of different ways to write a simple question. So lots of different ways to ask questions about shapes. Can use quantum numbers, can use the shape letters, can use the axes with the orbitals, can ask you to draw it. Lots of different options. Okay, so how to ask that question. We talked about past exams. I showed off. I think I answered the fact, so 4S versus 3D. I realize that's a different version, but in general, it's the same idea. I've seen some people that are like, the 3D should go first. We're going to write this in periodic table order. If you have to, so you're going to see us write 4S 2 and then 3D 10, whatever we're doing. What would that be for? Argon. More argon. They're going to see us write it like that in periodic table order. I do understand that a variety of different sources do it the other way. So if you have to write this out by hand on the back of the exam, we would also accept writing it with 3D10 and then 4S2. Both are fine. Because I forget which way Alex makes you do it, but I understand that like some AP teachers have you do it the other way. I don't know. As long as all the pieces are there. That's the goal. As long as all the pieces are there. So the question about metals, nonmetals, and metalloids. So we are allowed to ask you questions about nonmetals versus metals. Let me show you what I mean and why I'm saying it like that. So Here's the game. This periodic table that is in color has a key. It's down. Sorry. I'm about to color and highlight a key that is color coded. How about I not do that? Marker, red. The key is right here. So I realize in black and white that your metalloids don't get colored very easily. So we can ask you questions about metals, nonmetals, and metalloids, in which case that is present on my screen here because it's in color. You can actually see that there are orange ones that are metalloids, and there are blue ones that are nonmetals, and there are green ones that are metals. So we can ask you about those. What we have a tendency to do instead, though, is we usually don't ask you about metals versus nonmetals, and we especially usually avoid metalloids. We have a general rule, and it hasn't come up a whole lot yet, but it will in bits and pieces. If you Google metalloids, you will come up with different lists of what a metalloid is and which ones of these elements actually count as metalloids. Now, some of them will always be the same. Boron, pretty much always in the metalloid category. Silicon, always in the metalloid category. Silicon is the one that we use as the like, this is why the category exists. Silicon. So silicon, metalloid, sure. The rest of these, sure, yeah. The tricky part is that like the periodic table color coded makes you choose. This is a metal, this is a metalloid, this is a non-metal. And while some of these do fit in those categories perfectly, some of these don't. So we have a tendency to not ask you guys questions about metals versus non-metals for exam 1, because metal versus non-metal is something you will need when we go to name things and when we name compounds. And naming compounds is an exam 2 topic. So it is not bad to know where the metals and the non-metals are and to kind of get an idea that the metalloids are kind of over here somewhere. But we don't often ask about metals versus non-metals on exam 1. We especially don't usually ask about metalloids because we don't want to punish somebody who learned a certain list of metalloids in high school and then our list is slightly different. And the truth is that they're kind of mushy as far as those categories go. Things that we will ask you though, actually I'll just grab it off of my PowerPoint. So we won't necessarily ask you metals versus non-metals, but we'll ask you, what's my chapter 4? Chapter 4. Where's my slide with all of the stuff? It has all the labels. So many labels. This one. That's what I want. So this just has periodic table with a bunch of labels on it. So this has alkali metals and alkali earth metals and chalcogens and halogens and noble gases and lanthanides and actinides and transition metals. So these names you need. You need alkali metals and alkali earth metals and transition metals and chalcogens and halogens and noble gases and lanthanides and actinides. Lanthanides and actinides are actually already labeled for you, so I don't really feel bad, but it's small. Don't get me wrong, the print is very, very small. But lanthanides and actinides are actually already labeled. Transition metals actually are already labeled for you. It's small. It's very, very small, which means out of this list, you really only have to know alkali metals, alkali earth metals, chalcogens, halogens, and noble gases. You got five labels because the other 3, transition metals, lanthanides, and actinides, are actually already on the periodic table we give you. So those you need. You need those. We will use all of these titles for groups of elements, columns of elements, whatever they are, rows of elements, as we go along. So those names you need, those names you do need. So I babbled about metals and nonmetals and metalloids, exceptions to electron configuration. I am probably going to run out of time for the technique to go from grams to moles and moles to atoms, so that's probably going to be a thing in the follow-up video. Quantum numbers is definitely going to be a follow-up video because that'll take a while. Valence electrons, we'll see. Ionization energy, we'll see. Actually, valence electrons, do the quick version of valence electrons. Right now, valence electrons. There are two different ways to think about valence electrons. There is the technical definition way that is better. And so when we say valence electrons, these are electrons in the highest energy shell. So you are looking for the highest value of N for valence electrons. That's the goal, the highest value of N. Now, that's the technical definition. That is the definition that you need. I'll give you some examples of why you need that highest value of N. Let's look at these two, scandium and titanium, and their electron configuration. Scandium goes argon, always argon, and then 4s2 and then 3d1. Titanium is right next to it. It's going to go argon, 4s2, 3d2. Valence electrons are the highest value of N. N is 4. And that's the highest value of N. Both scandium and titanium have the same number of valence electrons because they've got 2. They've got 2 valence electrons each. I don't care about 3D. It's got a different value of N. 3 is less than 4. And the only thing I care about in valence electrons is the highest value of N. I only care about the electrons in the 4s subshell in these examples because the 4s subshell is the highest value of N. I don't care about those d electrons for valence electrons. No, I don't. So your definition of valence electrons is the highest value of N. Yes, we will use it like that. Now, the other thing to note about that highest value of N is on your periodic table, this says 3A, 4A, 5A, 6A, 7A, 7A. 8A. These are called main group elements, 1A, 2A. If it is in a group that has an A on it, then the number of the main group is the number of valence electrons. Now notice everything in the transition metals has a B, so it doesn't follow this rule. And they're those lanthanides and actinides don't have A's or B's. They got nothing. But if it's got an A, the number of the main group is the number of valence electrons. So for example, we'll do carbon and oxygen for examples. So carbon is technically, so for carbon, we'll just do 1s2, 2s2, and then 2p carbon, 2. So I'm looking for the highest value of N. For carbon, the highest value of N is 2. and I'm looking for all the electrons in the n equals 2 shell. That's 4. I got 2 electrons in the 2s subshell and an additional 2 electrons in the 2p subshell. Highest value of n is 2. I said 2 a lot. And if you look at where carbon is in the 4a. So it should have 4 valence electrons. 2 plus 2 is 4. So carbon has 4 valence electrons. When I turn to oxygen, 1s2, 2s2, 2p4. Now I'm looking again, highest value of n, that's 2. For oxygen, though, I'm adding 2 plus 4, which is 6. Oxygen is in group 6a. It's got 6 valence electrons. So valence electrons, if it's a main group element and it has an A at the top of the column, the number of valence electrons is just that number. If it's not one of those, though, then you need the definition. And the main group elements are following the definition. They just so happen to be labeled to make your life easier, but they're following the same definition. So the valence electrons are the electrons in the highest energy shell. So you want the highest value of n no matter what. So I know that that's a little weird, but that's where that comes from. That's what your valence electrons are. Exceptions. So exceptions. There are 5 exceptions that you are responsible for in electron configuration. They are chromium, molybdenum, copper, silver, and golds. Here's the way the exceptions work. I'm gonna grab my PowerPoint slides. Maybe. There. Yeah, because this just has, so chromium is expected to be 4s2 3d4, but it's not. Chromium is actually 4s1 3d5, 3d5. I'll show you. So chromium is right here. Chromium starts therefore at argon. And it's going to be 4s1 3d5. The D subshell, 1, 2, 3, 4, 5. The D subshell is more stable. All subshells are more stable when they are half full. Turns out that having a half full 3D subshell has a greater stability to it, and therefore it is more energetically favorable to have a half full subshell than it is to follow the Aufbau principle. So yes, this does in fact violate the Aufbau principle, but this is a known exception, and this is what we see reflected in real life. Chromium does have just 1 valence electron. Only 1 electron in that 4s subshell. So this is what we experience. Molybdenum, because it is right below it, is going to have a very similar idea, but molybdenum, which is right below chromium on the periodic table, same general idea, but then we're down 1, so this is krypton, and then this is 5s1 and 4d5. But same idea that we're looking at a half-filled D subshell demanding what's happening. When we go to the other set, what you're going to see repeated is that S1. So when I look at copper, this is then going to be still argon, and then 4s1, but now we're looking at a full D subshell. So we're basically stealing 1 electron out of the 4s to have a full D subshell. copper, silver, and golds. And again, this is very much what you see. Copper has a very stable electron configuration that has only one electron in its valence electron. Silver, this is definitely true for silver. There'll actually probably come a time where I refresh you guys on silver. And then some of you will be not mad at me, but perhaps not pleased that this whole full D subshell thing actually mattered. So those are the sets that you need. Is they are 5 times where having a half-filled S subshell so that you could have either, in the case of copper, silver, and gold, a full D subshell is more stable than following that Aufbau principle or the build-up principle. So these are basically stable. Nature uses these Aufbau violations. So they look like violations. They are technically Aufbau violations, but this is what we see in nature. So these are the 5 exceptions to the electron configuration of the periodic table that you are responsible for. So yes, you do need to know what they are. Yes, you also need to know that these are there because they're more stable. This idea that a half-filled D subshell has extra stability, is lower in energy, is also part of this. So the fact that you have exceptions to electron configuration because a half-filled or filled D subshell gives the atom extra stability. And by stability, we mean lower in energy. So whenever we're talking about these, one of the questions that often comes up is, do I need to memorize X? Please realize that if we have told you the reason why, you also need to know the reason. I understand you are going to memorize chromium, molybdenum, copper, silver, gold. Even though they're on the periodic table, you could probably look at the periodic table and figure out where they are. Do know that you need to know why they are like that. Not just that they are, but why. The fact that it gives the atom extra stability and it is lower in energy. There's more stability in that half-filled or filled D subshell. Okay. I've run out of time because it's 7 p.m. Are there other questions out of the chat that I can answer in the follow-up video?
Just a moment, be sure I got them all. But it looks like there's a few more questions. First one would be: Are we going to have to know all of the experiments, such as the oil drops and the gold foil studies?
Okay.
Next is: do you know if the organic chemistry tutor Gen Chem Part 1 video covers most of these topics?
That one I'll answer real quick. I still haven't gotten the time to watch any of these. I know previous students love the Organic Chemistry Tutor YouTube channel. I have to assume that they like it because it's useful, but I still haven't watched any of them. So valid question. Please ask some upperclassmen because I honestly, I don't know. I can't answer that question. I just don't watch those. I should, but I don't. But valid question. Valid question. Other things out of the chat.
All right. Next is: how do we calculate the valence electrons for the transition metals?
Okay.
And then the last question is: where will be able to access the playback of this video?
So the playback of the video, are y'all still going to put it on your YouTube channel? Do you still have a YouTube channel?
Yes, we will.
Fabulous. So the other place where it will also be is I'm back in the 701 section, and there's a folder now that says exam reviews. So we will go ahead and put the link to it in this folder. I think right now it already says future location of the recording. But it'll be a link to the Living Learning Community's YouTube channel. That's what it's going to link to, is their YouTube channel. And to the particular YouTube video is what that's going to be. Okay. Other things out of the chat.
Let me check one more time. That is all at the moment.
Fantastic. Then it is 7:03. So y'all have a wonderful evening and thank you so much.